So this talk is basically, is it not too loud? Is it okay now?
It's okay.
Okay. This talk is basically inspired by people using databases in the terms that we picking them in the same way we pick lunch. If we go to a lunch with our friends, basically we pick those dishes that we ate yesterday, or normally we eat, or we pick those that most of the people are getting. And this is basically the worst way to pick databases, since in most cases, this is the most expensive, most complex, and the element in the system, and also the element that has the biggest significance in terms of how your data will look like, in terms of performance. And now okay? Yeah, now okay. In terms of performance and so on. So yeah, basically this. Yeah, so who am I to basically judge you and your preferences in databases? I'm currently the lead of R&D in EcoVadis, and we are hiring, so come on. I'm running Cookies. It's a side project that you can, it's probably okay and running. I'm tweeting at Maclipsa, so if you have any hate or something like this, either you like it or you don't like this talk, go ahead. And the last, I'm blogging at Index Out of Range, and quite oftenly we're writing about databases. So yeah, so basically if we want to talk about databases, so we should first define what is a database. And we can go to the Wikipedia and look at the definition, but this is kind of boring. Let's do it in a kind of different way. Let's define some must-haves that a system will have to call it a database, and let's define some should-haves. So our must-haves. First, we should store data in a persistent way. Sounds kind of obvious, yeah. Next, we should be able to retrieve the data in a persistent way. So if we do two selects at once after each other, we should get basically the same amount of data. If there wasn't any data change and insert, it should be the same. And the last one, we should be able to delete data. So because after a year, it would be nice if our database wouldn't have a couple of petabytes of unused data. Should-haves. We should be able to query data. Now, what's the difference between getting the data and querying the data? Getting the data is basically by ID, like in key value stores, and querying is by any random field. So yeah, it's quite nice to do it. Next, updating data. Basically, updating can be done using a delete and then insert, but if we are using any relational databases or auto-generated keys, we are in a kind of trouble because this element won't be the same. So in this case, I'm saying about partial updates or the whole key updates. Next, transactions. And this is the part where people say, wow, a database without transactions. Actually, very small percentage of databases actually have transactions. I'm not talking about atomacy, I'm not talking about transactions. So doing multiple operations as one, basically. If any of them fails, the whole operation fails, and basically we can define what do we do next. Okay, so what's the simplest database? The lowest level you can get? Any ideas? Come on. You know the answer, so this doesn't count. Okay? Yeah, exactly, a file. Basically, why? Because a file is the building block of anything you can build upon. Any database, any system will eventually write to a file. So let's go and look at the files. From the must-haves, file is the definition of actually storing data in a persistent way. Yeah, because it's a file. We have the ability to retrieve data. Basically, it's a file, so yeah. From the should-haves, we have the ability to query data, and not only by the name, or we can also do it by path. In most systems have built-in functions to query by text in. So if it's a text file, it's quite easy and quite efficient. We can update files, and not only we can do partial updates. So say write this data from this byte to this byte. So it's quite awesome, and not all databases have it. And last, we have transactions. And even more awesome or less awesome, files actually support distributed transactions. So we can actually say, write this to the database, this to another database, and this file. If any of those three operations fail, roll back everything. That said, if any of you had any to do with distributed transactions, there's one to say. we can do it, that doesn't mean we should do it, because it increases complexity, time, and the number of errors you will get quite significantly. Okay, so let's complicate things a bit. Why? Because files are awesome, but if you have, for example, two machines, getting to the files via a remote server, or you have multiple processes, that kind of doesn't work. So we have to create an interface to do it in a kind of distributed way and do it remotely. So, but we won't be complicating that much. So let's go to a bit higher level. Let's go to key value stores. So basically, we have key and a value. Value is arbitrary. The database that doesn't care what it is. It's a blob from their side. So basically, it's quite simple implementation. For example, in case of files, we can basically calculate the hash of the full path, and that's it. So why do we actually do it? Those databases are ultra fast. They are the only faster databases are those embedded, basically those databases that run in the process. But in this case, for example, Redis is calculating their performance in nanoseconds internal. So yeah, it's quite fast. Next, they are scalable. Why? Because in most cases, these databases operate in a kind of multi-master scenario. So if you take, for example, relational databases, you have a master-slave database. So the slave basically waits until the master fails. Then it takes over. In this scenario, you actually have all the databases, all the servers are currently running, and that's it. So you are not wasting any computing power. They are simple. And why simplicity is quite awesome in databases? Because those things that are really complex become quite easy, like replication, adding nodes, and so on and so on. And this makes, for example, running them on production really easier and leads to less errors. So let's take the fastest one, Memcached. Basically, this presentation will be in a kind of way, I'm comparing databases, top 2 databases from dbengines.com, the ranking of mostly used databases, and grouping them by type of database. So let's look at the first one, Memcached, mostly used key value database. First, let's look at how are we connecting to the database. We have TCP/IP. So what this gives us, what this tells us, it tells us that we will be really fast, but actually we won't be able to scale or to be more fault tolerant. Why? Because if we would have, for example, TCP/IP is basically we do one request and come back. If the server fails, we can easily redirect it to another server. If we have TCP/IP, we have a constant connection. So it will be quite hard to route, but it will be quite fast. Next, data. First, it's completely in-memory database. Next, basically everything is stored binary. So if we have TCP/IP, we are sending data binary, and we are storing it binary, so it will be fast. It will be extremely fast. But if we are storing data in memory, what happens if we run out of RAM? And this is where LRU comes in. It's the last recently used item. Basically, if we have 4 gigabytes of RAM dedicated for Memcached, what will happen if we, for example, have 4 gigabytes taken and we send a 10 megabyte block? Memcached will take the least recently used block and delete it. Then take another one, until it finds enough place to store the key. So it's a database, but it deletes data. So it doesn't even fulfill the first item for storing data in a persistent way. But people are using it, and it's extremely fast. Yeah. Security as a feature. So basically this is opened, and it's not in a way of you have to check a checkbox. You have to add a DLL and compile it in a way that you have security. So if you open your data, if you put it on production, you can find that your data is missing, or either worst, it has been changed by someone. Not a good feature. Next, clustering. So the way how we go above one server and one database. In this case, we actually have shared nothing architecture. Why? Because this database is basically a hash table on remote servers. The client actually knows where he should send the data. So it's quite awesome. It's a very simple idea, but it's very, very fast. So why was it built? For caching data, basically, for mostly websites and so on. But sometimes people are using it as a database. Next, let's go to number 3, actually, in the most used databases. That's Redis. And the extension of the name actually tells us what it is. It's a remote dictionary server. So let's look at it. We again have TCP/IP, so we will be fast. We are storing data in a bit complex way because it's still a key value store, but we have types. Why do we have types, basically? For a simple reason. For finding bugs, because here we have proper clustering. So if we have conflicts, if we had two operations of add to list, there will be no conflicts. But if we are putting all the list itself, we'll have conflicts. So those list types, those data types, make it easier to resolve conflicts. That's all. And actually, make it easier, of course, also to store data. For example, the hyperlog-logs data structure is really good at storing very sparse probabilistic data. Look into it on Wikipedia. It's a really good article. And everything in Redis is a string. That's a very strange concept, but Redis is building upon this concept really awesome features. Like string operations. If you have the value is a string, Redis gives you the operations, for example, to replace in the value, add to value, or do any string operation on a remote server. Why is it awesome? Because if your value is quite big, you're not sending it. And if you're doing those atomic operations, they will be fast. You won't have conflicts. So yeah, they built a really interesting feature upon the basic concept that they've decided upon. Next, it's completely in memory. Redis has ways to store data on disks, but there are two ways, but none of them won't make you sure if someone basically takes the cable out of the server, you won't be up to date. Because all of those methods are asynchronous. The only way to actually, for Redis to be persistent, you have to have battery-supported RAM, which is quite expensive. And it doesn't make any sense. Pick another database. Clustering. And in case of clustering, Redis is quite an interesting architecture because it's auto-discovery, auto-healing. So if the node disappears, the cluster will take care of spreading data in this way that it's still okay. If you add a cluster, you basically run a Redis server with the name of the cluster, and it auto-discovers, auto-spreads the data across the cluster, and that's all. So simple again. Next, I'm seeing. Okay, Redis also has no guarantee of consistency. That means that there's a really tiny chance, and it's really described quite good in the documentation, that Redis will give you inconsistent data. Those writes you did eventually will end up in a bit different way. It's a very narrow chance, but it will happen. And master-slave. Redis has a very interesting way of spreading data because, as I said, all of the data is all of those servers are active, but we can actually do a tree-structure master-slave on replication. So we are not sending that big amount of data over the network, and we are more intelligent in a way. So and it has transactions and proper transactions, and we won't see those for a long time. And it has pops-up operations. Not that interesting for data science, but actually for running on production, it's quite good and it's extremely fast. Why was it built? For speed, basically. We are not having persistency, but we are having extreme speed. So what's the problem with those database? Why do we want to go further and basically complicate them more? In this case, if your value is a 50 megabyte object, getting it every time actually will be slow, and the database won't be slow. Your network will be slow, your application will be slow, and so on and so on. And we actually have values that are quite big. So again, let's complicate things a bit, but not that much. Let's add a select operation. What's a select operation? Basically, we can say which values, which columns we'll choose. So basically narrowing data. So basically going from this, it's a simple key value representation, we'll go to this. So we'll split the value part again into key value pairs. And this is what it's called basically a white table databases. White column databases. Do not confuse them with column databases because they are a completely different idea. But again, why do we do it? They are fast. They are not extremely fast because they know more about your data, so they will be a bit slower. They can narrow the data we are retrieving from the server, so we are not using the network. And if you are far away, that's a quite interesting thing to look at. They are scalable. We can still have multi-server architecture, so we are using all of our resources. They are simplish, I would say. So running them on production is a bit more trickier, but still quite nice. And we have data types. So we can check out our data if it is in the same type that we assume it is. So a bit more description. We don't have to have additional documentation about what's in the values. We see it in the database. And we have partial updates in some really narrow cases. And we have querying because we know actually what's happening. We know the types. Very, very simple querying. So the first and the most popular database in this case is of course Cassandra. And if we look at the data, we have compression. And why do we have compression in Cassandra, and in which cases? So basically, Cassandra is actually built by AWS, Amazon, in the case of implementing the shopping basket. What's the simplest way to implement a shopping basket? It's actually to have as a columns the product, and as values the number of items you actually want to have. But if we were to do it in a relational database, we will end up with huge joins, really, really huge joins over millions of elements, or in object database and so on. But if we do it in a wide column database, we can actually, when storing, we can actually ignore the products that have null or zero, because actually the application knows what are the all possible values. So if we have really sparse data, this database is really, really good because we are using only the actual part that we need. So from a couple of millions items to 4, max 10, basically. That's it. Next, querying. First, Cassandra had MapReduce, then introduced SQL. SQL is basically SQL with only the select part and very, very simple where part. Of course, we don't have joins. No way. As for clustering, this is where Cassandra actually shines in, and it's actually the main reason why people choose it, because it's fast. The architecture of Cassandra is basically a ring architecture, so we can quite easily add any nodes to the ring, and basically it extends. Another quite interesting thing with ring architecture is basically we can have consistency. The consistency can be told by the application. So if we have 5 nodes in a ring, we can say write this data to one of the nodes, or we can write it to all 5 of the nodes and wait for the replication. So if we want to be fast, we write it to basically one node. If we really want to have consistency, we wait a bit longer and write it to all of the nodes. It's quite awesome. And this gives us fault tolerance, but it also gives us one problem it's the biggest problem, basically. If you Google Cassandra problem, it's the first item. Cassandra isn't row consistent. So if you have 2 operations on the same row, Cassandra will and you have some kind of they are touching the same column, Cassandra will pick. We will have to choose which data to choose actually, and Cassandra will pick, and that's true, the lexically biggest. So it will sort the values and pick the value and insert. So Cassandra is actually atomic on updating each column, but update as we see from the application, basically from this key, update those columns. No, that's not the way it works. This gives us actually the speed of Cassandra, but it's the number one problem in people running Cassandra, and it's the number one problem when people are using a database and not reading any basic documentation, and then they have really big problems. And of course, this gives us that from the cap theorem, we are not choosing consistency, we are choosing availability, but because Cassandra is really fast and will almost always give us an answer. This answer may not be consistent, but hey, that's a type of database. Next, and it's also, of course, built for distribution. Now let's go to a completely different scenario. We have HBase, and actually the man from the Google talked about it because it started there. So a database over Hadoop. So in this case, let's think about what are the main cases, basically. If we are talking about Hadoop, we are talking about huge data sets. So that's awesome. So and you will see actually how those basic ideas evolve in this application. Basically, data. It's row consistent, and the data is versioned. And it's, of course, pretty good for any sparse data as any white column databases. But let's get back to row consistency and versioning. How does actually a database work? It actually writes the document as a whole each time, because it assumes that, hey, we're dealing with gigabytes, petabytes of data. So if I add a document that has 10 megabytes additionally, that's not a big of a deal. And I'm only reading from those documents that have the maximum version. And I'm cleaning those documents that are not up to date, basically, whenever I can. Why is this really awesome? Because any kind of disks, basically, maybe not SSDs, but basically those hard drives that we are using for really big amounts of data, they are really fast at writing, but they're really, really slow at seeking data. So basically, writing bits here, bits there, and so on and so on. So if we are writing 10 megabytes, it's really fast. But if you are writing a couple of kilobytes in different places, it will take a lot of time, and we'll use the drive. So yeah, that's it. Because we are running on top of Hadoop, this is how this database works. And for querying, we have drill, also talked about on the keynote, and we have extremely fast reads. Why? Because we built upon a reporting system, but the writes will be quite slower. As for clustering, it's quite complex, and basically running Hadoop A-base is quite complex. We have Zookeeper. We don't have any transactionality, but of course we have consistency, because yeah, if we have our reporting system, the availability, we can go down a couple of times, but we really have to be consistent. And for what was it built? Of course, for reporting. And the last, not that well known, but quite an interesting view. Also, a white column database also runs on top of Hadoop, but basically has one really unique feature. And remember that we are talking about petabytes of data. You can give privileges to each column to each cell in the database. So let's imagine what company has really high security management and has petabytes of data. Someone? Any ideas? The NSA. Actually, NSA developed this database in-house and gave it to the Apache Foundation. You can actually now use it as any normal Apache Foundation database. Of course, for what? For security. And again, those are three databases that are the same type, but they behave completely different. They have completely different usage, and so look at them. And basically, what's the problem? Why are we going even further and even further? Because we have quite fast database, we can query and so on. It basically looks awesome. Because naming of things is really complicated. If we go to more complex types, it gets really complicated. So let's complicate things a bit. Not that much, but only a bit. Complex data types, like lists and nested objects. Imagine modeling a list in a white column database. You will actually have the indexes. So that gets quite complex, for example, counting the elements and so on and so on. And nested objects, yeah, you will have a lot of dots. That's not nice. So let's look at the most popular object database. Mongo, of course, the most used database in case of object databases. And, it's not synchronizing. Okay, as for data, it stores data in binary JSON, and basically it has data types, which is quite nice. But what's actually the hardest part? If we actually wanted to implement an object database, what's the hardest part? It's actually storing data types of variant length. For example, because if we have a file, know the structure, we can actually do quite simple things. Read from this byte to this byte, it will be our amount, for example. But if we have a table, that's quite complex because we don't know where this table ends. So Mongo just said, you won't have any variant length types. The collections the size of the collection have to be told upfront. And for querying, we of course have dot notation. because we're talking about object database, we have where operations, and not only those simple operations, but we have operations for dates, because comparing strings is quite easy, but comparing dates, smaller or bigger, you actually have to understand the type. So yeah, we have it. We have explain for profiling. We didn't have explain for profiling in any other previous databases because there was no need. And here we get quite complex, so we should be able to explain why is it running quite slow. And finally, we are quite complex, but we don't have joins. Why? Because those are completely separate documents, basically. Clustering, sharding with asynchronous replication. What does it mean? That basically, if we have 10 Mongo databases and we write to the master, the only way to read accurate data is from the master. The replicas only have asynchronous replication, so we can read from them, but there is no guarantee that the data will be up to date. Sounds good? So. And why was it built? For speed in distribution. It's fast, it's distributed, and that's all. Consistency, not that much. Next, AWS DynamoDB, also quite popular database, and let's look at the use case. For example, it's a SaaS product, so basically you can't have it on premise, and you have to actually go to AWS and pick a slider and actually tell the throughput. Data, we don't have a schema. The row can only have 64 kilobytes. That's not much, I would say. There's 1 megabyte limit on the query, and after it, data will be basically cut. And we have limited checks on data. So basically, we can declare it, but database, when returning, won't check if the data that's being returned is with the proper type. For querying, we have no secondary indexes, so it won't be fast. Of course, we don't have any complex queries, no joins, nothing at all. And it's priced on throughput. And this actually gives us the answer, why do we have all of the above? Because Dynamo is basically, if you want to buy Dynamo, you go and you see a slider. How many operations a second do you want to have? And basically, as you move the slider, the price increases, and that's all. And AWS guarantees that you will have this throughput. Why do we have this restriction? Because it's running on AWS infrastructure. If they want to guarantee the throughput, they have to have those limits. It has to be a really simple database. It's basically a speed as a service. That's all. Let's make things a bit more complex. Joins. Actually, this Google is always suggesting me that I meant not joins, but something different. So yeah. Why do we actually? Let's complicate those things. Why do we actually want to complicate? Because things are connected. In most cases, we want to find the meaning between a couple of collections. We want to have, we want to see how this compares to this and so on. So the connecting part is quite important. And one thing to note in here, we are on a Python conference. There are wars between multiple languages, which is better, faster, more awesome, more hip, and so on, so on, so on. Those wars are completely nothing compared to wars between different types of databases. You will see Oracle fans destroying SQL fans, and the guys from MySQL saying that those databases are priced way too much. Most of them, let's put it lightly, are not telling the truth, or are telling a very limited scope of what they know about the other database. Really dig into the documentation and see what is happening. And in here, basically, does anybody know how long do we have relational databases? How old are they? Very good. About 45, something like this, basically. So we put billions of dollars into those databases, so you would assume that they are more or less the same. They are not. Basically, let's look at, for example, versioning. Versioning, basically, we have MVCC and log-based. Why is it important? Because log-based databases are really better at write-heavy operations, and VCC are really better at write-heavy operations. And the MVCC will actually, if you see, for example, that the SQL server is killing your disk, using DynamoDB, yes, this is exactly MVCC, basically, because it has to persist those transactions on disk. Yeah. Next, memory tables, because now we have having half a terabyte in RAM is not that big of a deal. So actually, what providers made data. Let's put this relational data in RAM storage, and let's do something with it. And Oracle said, yeah, let's do reporting on those tables. MS said, no, let's do online transaction processing. So let's do normal operations. Let's make those RAM tables behave like normal tables. Two completely different views. And of course, MySQL said, no, that's too expensive, we won't do it. And the other guy said, no, let's fork the database. And they made MarianaDB, which of course supports, which is a column database. Next, as for scaling, Oracle says that they have rack. I didn't use it. The other one, basically, you have sharding, completely different architectures. For column indexes, what are column indexes? If you have sparse data, for example, all data that you are grouping upon, basically you can treat them as a basically dictionary. So in the rows, you will only have the IDs and the values will be stored in a separate dictionary. This is really, really awesome for querying, aggregating data. And SQL Server said, yeah, let's implement it. And Oracle said, nope. Transactionally full in those two biggest ones. But in MySQL, you actually will auto-commit transactions, and the other engine will say if you are doing transactions across multiple tables, then you don't have any transactionality. Yeah, this database is for free. Remember that. Next, CTE. CTE. What's basically this is the way if you have a structure that is hierarchical and you don't know its depth. Using CTE, you can basically have recursive queries that will go all the way down until you have the whole tree. You have it in Oracle and SQL Server, but in MySQL, no. So you will, from doing one query, you will do multiple queries as many layers. Yeah, and that's it. So what seems to be the problem? We have almost anything we want currently. Reporting. Actually, how many of you have actually heard that? Yeah, I want to have this report by the end of the day. Yeah, one person. Yay! Okay, so let's this time flip things a bit by 90 degrees for fast reporting, for aggregation, compression, and basically having fast writes by the cost of reads. The other way around. We have Teradata, and Teradata is quite an interesting database. They exist for 30 years, and to give you a scale of database that we are talking about, Teradata, in case of Walmart, one table has more than 1.5 petabytes of data. One table. That's quite a lot of data. Yeah, in case of data, you basically have column and row. So basically you are storing, in the case of column storing, you have a separate index and you're storing only IDs. So that's really fast for aggregation and querying. And you can also read the JSON. But you have limits on some types of values, and it's a really simple database in this case. You have ANSI SQL because those database costs are really a lot, but if you want them, you don't have the ability to choose. So yeah, don't count on features. And it works with Hadoop. Why? Because we are in the world of reporting, so it will work. On the other side, we have MongoDB. It's free, so it's nice to see. As for the data, we have purely column-oriented data. For querying, we have SQL support, and we have database cracking. So the database is able to re-index the elements as they are used. So we don't pay the cost upfront on writing always. And we have GIS support, CQL support that's for arrays. We have for some BAM support for sparse data, I think, and the RDF is basically graph querying. And we have support for RPython. And if you are looking for really big data sets, look for this database. Basically, because for example, human genome, the big Hadron Collider, yeah, they are storing in this database. And most academic usage. Don't count on documentation or phone support or any kind of this way. But what seems to be the problem with those? We covered all of the databases, so why go any further? Actually, actually searching. connecting. Basically, if you want to connect data, if you want to find connections, those databases won't be that good. So let's flip things a bit, basically. Let's concentrate on connecting data. Basically, graphs. And if we go into this case, what is the interesting part? Paths, connections between two different nodes that we don't exactly know the structure, for example. And hierarchical data, for example, genome and so on. And there's a quite nice saying that if your relations is the data, go with those databases. Titan, there's a basically division that you can have graph as reporting and graph as operations. This is basically reporting. Okay, I'm finishing. Sorry. Okay, so basically you are building here upon multiple storage engines, and the way the capabilities are made from the storage engines. So we can actually, for querying, we can have Tinkerpop. We can have very simple graph querying. We can have Spark, Hadoop, HBase, and so on. We can have Solr, Elastic for clustering, distributed, because we have large amounts of data, basic transactionality, built for reporting. Neo4j, completely different database, open sourced data, complete graph engine. It doesn't have any schema, so we can easily extend it. For querying, we have Cypher, a really awesome engine for querying graph data. And we have transactionality, again, for the second time, actually. For clustering, master-slave. It's a basically relational database for graph databases. And built for online transactional processing. The problem, actually, searching. And so let's flip things a bit, actually, for searching by another 90 degrees. So what we go, now we have indexes, basically Lucene. And those are not databases. If someone is saying that they are storing data in Solr, this data can quite easily disappear. Solr, basically, those are two databases that are based upon Lucene, so the same search engine, and they have really minor but quite important differences. Data, XML and JSON, yeah. Querying, Lucene queries, if anybody used them, quite obvious, and basically they work. We have group by, and this is the distinction. We can group by multiple servers in the cluster. Solr doesn't have it. Clustering, quite complex with Zookeeper, but we can increase the shards. This is a really minor technical detail, but if anyone will use Solr or Elastic, go into it, read in the documentation, because it's quite important. Open source, at real open source, anyone can contribute. Elasticsearch. Data, we only have JSON, because we are more hip and we are newer. Querying. Lucene, and of course also an extension that basically gives us some capabilities, really minor. For clustering, constant number of shards, and it's auto-clustering, it's really easy. Yeah, auto-balancing, and the cluster behaves more or less like the Redis cluster. But the open source is only read-only, you can only contribute if you are the employee of Elastic company. Yeah. Are we there yet? Yes, we are finished, but there are really a lot of more databases. What are the lessons? Databases are like chili peppers, neck peppers. If you don't know which to choose, really think multiple times and check it, because it can really hurt. Next, you can't have everything, basically. There's no golden bullet, there's no one solution, but you can have multiple databases. And choose those databases that are perfect for the questions you will be answering. Lesson 3, there's no SQL database. There are differences, and the differences are quite important. Read upon them, and basically, yeah, check them. That's all. Sorry for taking too long. Yeah.
Okay, we're running out of time a little bit, so I think we have time for one questions, and the other ones will be at the after party that I invite you really. So do you have any question now? Okay, so I just want to invite you to... Oh, we have one question, okay.
I wasn't going to, but there's a graph database in Python called the ZODB. What do you think of it?
I haven't been using it, to be honest, basically. I would have to read into it, but basically, Neo4j took over the market. They are way ahead of everything. They are most universal. They have Cypher. And if I would have to use Tinkerpop or any the simple low-level languages for querying graph data, it doesn't make any sense. Because if you go to Cypher, you go to a version of basically SQL. And the power of querying, the power of being really clean about this querying, that's the power that we should be using, and not going from node to node and then doing all the operations by ourselves. It doesn't make any sense in my case. That's all.
Thank you.